Hello students, welcome to Marine Engineering Tutorials. I am Atul Kumar Gupta and back with a new tutorial. We are presently studying marine boilers. Today we have 36th lecture and the topic is reaction of marine fuel elements with oxygen. Both the liquid and gaseous fuels of petroleum based are used in marine boiler furnace. Liquid fuels used are diesel and heavy fuel oil, whereas natural gas is the gaseous fuel. Carbon and hydrogen are the main constituents in marine fuels, although sulfur is also present, for which the limits have been imposed since 2020. Theoretical amount of air requirement, also called the stoichiometric air-fuel ratio, is worked out for complete and efficient combustion of fuel through the following slides. Composition of petroleum. This table shows the average composition of liquid fuels used on ships. The fuel may have average higher calorific value of 43,300 kJ per kg and maximum density of 991 kg per meter cube at 15 degree centigrade. The liquid fuel may contain 85% carbon, 12% hydrogen and 3% sulfur, which take part in chemical reaction with oxygen. Nitrogen present in the fuel or entering in the furnace along with air does not take part in the combustion process, although it takes away some of the furnace heat. Oxygen has a small percentage in fuel which is ignored during the calculation of stoichiometric air-fuel ratio. Metals forming a small part of fuel are left as residue after the combustion. Whenever high sulfur fuel oil with sulfur content more than 0.5% is used outside the emission control areas, ships should be equipped with exhaust gas cleaning system. However, within emission control areas, the fuel in use should have sulfur content less than 0.1%. Calculation of stoichiometric air-fuel ratio for heavy fuel oil. The stoichiometric air-fuel ratio is the ratio that gives the amount of air required for complete combustion of the unit amount of fuel. One atom of carbon burns with one molecule of oxygen and forms one molecule of carbon dioxide. Substituting their atomic weights in the equation, we can say that 12 kg of carbon combines with 32 kg of oxygen to form 44 kg of carbon dioxide. As carbon percentage in the fuel is 85%, oxygen requirement for burning 0.85 kg of carbon can be worked out as 2.67 kilogram. Four atoms of hydrogen burn with one molecule of oxygen and form two molecules of water vapor. Substituting their atomic weights in the equation, we can say that 4 kg of hydrogen combines with 32 kg of oxygen to form 30 kg of water vapor. As hydrogen percentage in the fuel is 12%, oxygen requirement for burning 0.12 kg of carbon can be worked out as 0.96 kg. One atom of sulfur burns with one molecule of oxygen and forms one molecule of sulfur dioxide. Substituting their atomic weights in the equation, we can say that 32 kg of sulfur combines with 32 kg of oxygen to form 64 kg of sulfur dioxide. As sulfur percentage in fuel is 3%, oxygen requirement for burning 0.03 kilogram of sulfur can be worked out as 0.03 kg. Total oxygen requirement to burn 1 kg of fuel is the total sum of oxygen requirement to burn 0.85 kg of carbon, 0.12 kg of hydrogen and 0.03 kg of sulfur, which is 3.33 kg. As the percentage of oxygen in air by mass is 23.2%, total air requirement to burn 1 kg of fuel is 14.35 kg. Composition of natural gas. This table shows the average composition of natural gas used on the ships. Natural gas was earlier used as fuel on liquefied natural gas carriers to deal with the cargo boil-up gas. Its use has recently been started on other types of ships too, as it is a clean fuel and serves as an alternative for low sulfur fuel. Methane is the main constituent of natural gas with 94.9%. Ethane with 2.5% and propane with 0.2% are also associated with it. Iso and normal butane, iso and normal pentane, hexane plus and hydrogen with very small concentration are ignored during the calculation of stoichiometric air-fuel ratio. Nitrogen and carbon dioxide do not take part in the chemical reaction, and oxygen with its small percentage is ignored during the calculation of stoichiometric air-fuel ratio. Natural gas may have average higher calorific value of 55,559 kilojoule per kg and specific gravity of 0.7158 kilogram per meter cube. As natural gas is stored in liquid state at minus 162 degrees centigrade, it has to be heated to about 30 degrees centigrade before its combustion in the boiler furnace. Calculation of stoichiometric air-fuel ratio for natural gas. The stoichiometric air-fuel ratio is calculated on the molecular level. The stoichiometric ratio gives the exact amount of air required for complete combustion of any fuel. Actually, about 10 to 20% of excess air is additionally required for efficient and complete combustion of fuel. One atom of methane burns with two molecules of oxygen and forms one molecule of carbon dioxide and two molecules of water vapor. Substituting their atomic weights in the equation, we can say that 16 kg of methane combines with 64 kg of oxygen to form 44 kg of carbon dioxide and 36 kg of water vapor. As the percentage of methane in natural gas is 94.9%, oxygen requirement for burning 0.949 kg of methane can be worked out as 3.8 kg. Two molecules of methane burn with 7 molecules of oxygen to form 4 molecules of carbon dioxide and 6 molecules of water vapor. Substituting their atomic weights in the equation, we can say that 60 kg of ethane combines with 224 kg of oxygen to form 176 kg of carbon dioxide and 108 kg of water vapor. As the percentage of ethane in natural gas is 2.5%, oxygen requirement for burning 0.025 kg of ethane can be worked out as 0.09 kg. One molecule of propane burns with 5 molecules of oxygen to form 3 molecules of carbon dioxide and 4 molecules of water vapor. Substituting their atomic weights in the equation, we can say that 44 kg of propane combines with 160 kg of oxygen to form 132 kg of carbon dioxide and 72 kg of water vapor. As the percentage of propane in natural gas is 0.2%, oxygen requirement for burning 0.002 kg of propane can be worked out as 0.01 kg. Total oxygen requirement to burn 1 kg of natural gas is the total sum of oxygen requirement to burn 0.949 kg of methane, 0.025 kg of ethane and 0.002 kg of propane, which is 3.9 kg. As the percentage of oxygen in air by mass is 23.2%, total air requirement to burn 1 kg of natural gas is 16.8 kg. Stoichiometric air-fuel ratio for different fuels. This table shows the stoichiometric air-fuel ratio for different types of fuels used on ships and in automobile sector. Diesel oil is used as the pilot fuel in boilers and engines during starting up and subsequently changed to heavy fuel oil. Gasoline is mainly used in automobiles but is occasionally used in ships, rescue lifeboat equipped with an outboard engine. Natural gas is used in hybrid automobiles and as cooking gas in homes. It is now coming up in a big way as an alternative for low sulfur fuel on the ships. Use of methanol was earlier started in automobile sector to reduce the dependency on petroleum. This has now been replaced with the ethanol which is used to blend with gasoline. It is derived from biomass instead from petroleum. When the air-fuel ratio in the mixture is less than stoichiometric air-fuel ratio, it is known as rich mixture and results in black smoke. Similarly, if the air-fuel ratio of the mixture is higher than the stoichiometric air-fuel ratio, then this mixture is considered as lean mixture. A slightly lean mixture with 10 to 20% excess air is preferred for good combustion. This completes the study of various types of fuels used on the ships and the reaction of their elements with oxygen to find the stoichiometric air-fuel ratio. This book is written by me and covers all the topics as per Indian Maritime University syllabus. It is also recommended by Indian Maritime University as a reference book. It clarifies the concepts with simple illustrations. This book also provides answers to all the questions which have appeared in the examination conducted by Indian Maritime University. This book can help the students in preparing for the exam and also to work on ship boiler safely. Hope you have liked the lecture. You can write your feedback in the comment box. If you have liked the tutorial, you may share it with your friends. You may subscribe to the channel for getting notification about the new tutorials. I will be back with a new lecture shortly. Thanks for watching till the end.